So the next speaker is Dr. Christopher Rowley. So he's a postdoctoral researcher at McGill University.
Hello, I think everyone can see this. Let's see here. So thanks for listening to my talk. I'm going to talk to you about optimizing ihMT imaging for the cortex. So it's obviously not myelin water fraction imaging, but we sort of share the same goal in trying to come up with a myelin-specific metric. So a little bit of background on MT imaging or ihMT. It's an emerging contrast that is proving to have increased specificity for myelin content, and it's been shown to increase linearly with myelin-basic protein staining. The contrast itself originates from differential saturation of the dipolar pool from single versus dual frequency saturation pulses. And recently, the feasibility of using ihMT in the cerebral cortex has been demonstrated, and a boosted saturation approach, which applies multiple saturation trains per TR, has been suggested for obtaining an optimal SNR. But there's no real consensus on the optimal parameters to use for imaging, and this could depend on the time available, human versus animal imaging. So what we're really interested in, if we put in some constraints and we wanted high resolution 1 millimeter imaging, what would that protocol look like? So we know MT can be modeled using two pools. So we have a free water pool and a semi-solid pool, and we can increase the fitting accuracy by adding a dipolar pool to the semi-solid pool. And the ihMT contrast really originates from this few percent difference we can achieve, which is really driven by this omega times the saturation rate term. So if we look at what those equations look like, we don't really have time to get into them, but we have the first three equations which govern the water pool, the bound pool's Zeeman orders, number 4, and then this dipolar pool here. So again, we're interested, I mean, all of the variables are going to impact your signal, but our contrast is driven really in this pool. So the saturation rate of the bound pool is governed by the square of the applied radio frequency we're applying. So if we increase our B1, we can get more saturation. And then our line shape in human tissue, it's generally super Lorentzian, and that's a function of the offset frequency that we're applying our pulses at. And then our omega term here is proportional to this offset frequency. So you can see you could potentially have more saturation with a higher offset frequency, but if you were to plot this line shape, it actually decreases. So some early work on ihMT by the Pharma al. Showed that the ideal offset frequency for ihMT imaging is around the 7 to 8 kilohertz offset. So those two are gonna play with each other. So for this study, we use numerical simulations. We have a few constraints. So it's been shown that you're going to want to run this close to the SAR limits of the scanner to get the best contrast possible. We fixed the time gap to 0.3 seconds between alternating pulses. Again, from the last slide, offset frequency of 8 kilohertz. And because we want a reasonable scan time, 4.5 minutes per image, and we need 3 images. So for the study, we used a custom-coded TurboFlash sequence with an MT prep module. For high-resolution imaging, it's to get a fast image, we're going to play with the turbo factor, so how many lines of data we can acquire per TR. And then for generating the contrast, we can adjust the time of the pulse for the saturation, the number of saturation pulses applied per train, and then the number of trains applied, this N boost or boost factor, and then sort of the spacing of those pulses, TR-MT, for each prep module. And sort of the parameters that were looped through are displayed here. So of importance, because we left everything open, this led to almost 8,000 different sequence parameters that could be used for a non-boosted approach compared to over 200,000 with a boosted approach. So quite a few options if we left it quite open. Quickly going through, we did some in vivo imaging. We had 2 subjects scanned with 3 different data sets or 3 different protocols for ihMT. For MT side imaging, you need a T1 and an M0 map. So we used an MP2H to get those values. And the main difference between these 3 protocols was we increased the TR to sort of just look at the different parameters we're interested in. as well as increasing the turbo factor from 880 to 200, and then with that also increasing the saturation. But all of these images are acquired right around that 4.5 minute threshold that we set for the study. So we wanted to make sure our simulation results were going to match with the data we were going to acquire. So again, 3 protocols were required, 2 subjects. The MT-SAT maps were generated, and we corrected only the B1 plus inhomogeneity for the excitation pulses, leaving it in for the saturation pulses. Cortical surfaces were generated with FreeSurfer, and we extracted the MT-SAT values where the T1 observed was around 1400 milliseconds, just to fix another parameter in this. And then simulations were performed over a range of tissue parameters taken from the literature. And then we went with the fit parameters that had the lowest mean squared difference. So what this looked like from the data, so this is the subjects pooled. The single includes the average of the positive and the negative offset frequency images. So we do have good correspondence with our fit parameters and our MT-SAT data at both the dual and the single offset frequencies. Of note of the parameters, the T2A didn't have a huge impact on the fit quality, so I wouldn't read into this parameter too much. The R1 observed, again, was fixed. R1B is typically fixed at 1 second inverse, but we found it had a slightly better fit, specifically at the higher B1 RMS values. And then sort of the biggest difference that we found was this T1D value. Typically in the more recent ihMT work, it's been around 6 milliseconds. It didn't quite fit our data set, but it does align with the previous work in QMT, where it was found to be around 0.7 milliseconds in the white matter. So how do we look at the data set? So we've simulated over 200,000 protocols, and we want to see what's the best SNR we can get. So the plots I'm showing here, it's if we fixed any 2 parameters, what is the best SNR you can get? So everything else is completely open. For each of these data points, the gray points represent something that didn't quite meet the time cutoff. So what we see is a non-boosted approach definitely has a lower SNR than the boosted approaches, but we do see an ideal saturation parameter region with a TR of around 100 milliseconds, 6 to 8 saturation pulses, and a low turbo factor of around 10. The boosted SNR, again, increases with increasing turbo factor, TR, and the number of boost trains. And there appears to be an optimal combination with a lower number of saturation pulses of around 6 to 8 combined with the high boost factor. So because we use a centric out encoding, we're going to have a loss of achieved resolution due to the change of magnetization over the readout. So you're getting less weighting towards those high frequency components in k-space. So we simulated the k-space data and looked at the resulting PSFs. And as you might expect, we definitely get a broader PSF with the higher turbo factors compared to a lower one when this is pushed out to the ihMTR. And you do get a slightly taller PSF, but you still can get the best sort of SNR with a boosted approach. And improve it going on with that, if we added noise to our simulated case-based data and looked at the SNR, we do see increasing SNR over increasing turbo factors. So as you go up in turbo factors, the points are getting higher and higher. But that comes at the cost of decreased achieved resolution. So there is a blue line here, and that is representative if we took the yellow plot of a non-boosted approach as a reference, and what would the SNR be if we just increased the resolution, because the SNR is going to be a function of the voxel size. Because all of these points are above this line, we're seeing increased SNR from this boosted approach that's not explained by solely increasing the voxel size. So what does this look like in the data? So this is the data set that was used to fit the tissue parameters. We have good SNR and the dual MT-SAT maps. There's some blurring that can be seen already at this level with increasing turbo factors. And we do see this significant increase in SNR as we move across the turbo factors in the ihMT SAT maps. But there is some obvious blurring, especially at the gray matter, white matter boundaries. So looking at this on the cortical surface, we use a non-boosted imaging approach just to see what it would look like. It is a lower SNR approach as predicted by the simulations, but we still see some of the highly myelinated regions of the brain popping out, such as the motor and somatosensory regions in the individual subject level. At the 25 subject group average, I think it looks pretty good. It resembles closely a quantitative R1 map or a T1 divided by T2 map, some of the other maps that are out there that suggest correlation with myelin content. And we're also suggesting you could improve the SNR by using a boosted approach for saturation with a moderate turbo factor to maintain some of that resolution. So the conclusions from this work are larger turbo factors are necessary for high resolution ihMT sat imaging, as low turbo factors result in too low of a B1 RMS due to SAR constraints to generate a strong ihMT signal. This was found by Helms at ISMRM. An optimal balance exists if you're not going to use a boosted approach with an optimal TR and saturation pulse scheme found. And boosted saturation schemes have a trade-off between SNR and effective resolution, but do definitely give you a boost in ihMT SNR over a standard saturation scheme. Thank you.
All right, thank you, Chris. So are there any questions in the chat?
Not at the moment.
Okay,